Assalamu alaikum. Hello viewers. In this tutorial we will be discussing about design of cams, and we will be having a simple design of a roller follower cam. For some introductory informations, cam is usually a rotating machine element which is producing a reciprocating and oscillating motion to another element, which is commonly known as follower. Usually the cams are rotated at a constant speed by camshafts, but the follower motion is predetermined and will be according to the shape of the cam. Even though this is a very simple mechanism, this is one of the most important mechanisms yet now for the engines mostly used to keep them operated, and in some cases even for compressors as well. Cams can be classified depending upon various elements, like they're according to the surface in contact, and that would be depending upon the type of the follower. The followers are many of the types, like knife edge follower, roller followers, spherical faced followers, flat faced followers, or some other types as well. But in most applications we might just see roller followers or spherical faced followers, since they produce lesser amount of friction. Even though the contact is a line, a knife edge or a flat face follower usually produces a higher amount of friction. So we try to go for rollers or spherical faced ones, and according to the path of the motion of the follower, they can be divided in mainly two categories, which are of radial followers and offset followers. They are defined for specific motions like simple harmonic motions or oscillating motions like that. So in this tutorial we'll be using one of the most simplest kind, and at first we will be generating a displacement diagram of the follower and using it to produce the cam profile. For that we will be following one of the problem statements here stated, and I've prepared it from one of the mechanics of machinery's books of mine. So it's just for an example that we'll be following. So it says that a cam with a minimum radius of 25 millimeters rotating clockwise at the uniform speed to be designed, and these are the basic specifications we need to consider. And since every full rotation produces 360 degrees, we will be dividing that angular path into stages depending upon the situation of the followers. So it says to raise the valve through 50 millimeter during 120 degree rotation of the cam. So for that we'll be just plotting a simple displacement diagram depending upon those problem statements, and we'll be deleting it later on in our sketch. And this sketch would be used only for the ease of our drawing and for more precisions. Usually cams are designed in these ways, and if you want you may check for some of the mechanics books as well. So let's see. To raise the valve volume through 50 millimeters during 120 degrees rotation of the cam, we will be assuming that this is a simple harmonically oscillating follower. So for that we draw a line vertical, and for ease we just change the dimension system. Edit this would be 50 millimeters, and this is the standard procedure I'll be following. For simple harmonic oscillation we make a circle whose center would be the midpoint of this line. Now we divide this circle into even numbers with equal spacing at this curve. So let's say we want a center line which would be like this, and now we make a circular pattern. In this the entities would be this line, and the point would be this one, and will not be rotating 360, rather it would be 180 degrees, equal spacing. The number of it would be, since we want to divide this one into even number of sections, so we need an odd number of lines. So this is good enough for us. From these intersection points, we produce horizontal lines. For that, let's just say we make a line in this direction. This would be the total distance covered by the cam in rotational direction. That would be in angles. So let's say we want points through these intersection points, but for ease we just pull them and make them intersected. This would make things a little more easier for us. So let's just draw some lines. All of them would be horizontal lines. There. For simplicity, we'll be using this dimension to be proportional to 360 degrees. So for that, let's say we say this would be 360 millimeters, and make these points all in a single line. There. We just hide the relationships. Much better. And now in our statement, since during first 120 degrees it's gonna rise for 50 millimeters, so we divide this 360 millimeter line into three parts, where the first segment would be 120 millimeters. So let's say we connect this one, this one, and this one. And now dimension them according to our needs. Now text, the second statement says that the valve is fully raised or fully open to next 30 degrees. That means this distance would be 30 and the other ones would be lower. The valve would be lowered in next 60 degrees. So we make another line and dimension it 60, and the other part is the rest of the 150 degrees. So now what we do is divide these segments as equal number of segments that we have done in this section. We have divided it into 6 sections, so we produce this segment into 6 parts. So similarly, we pattern something like this area, this line, and since we need 6 divided segments and the intermediate distance would be 20 millimeters, let's say we need 6 lines with each 20 millimeters separation. So let's hit OK. Similarly, in this section we need the same amount of segments to represent the lowering of the follower curve, and for that we just pattern this line with this one and with this one only, and this would be 6 as well. Now if we want to see the path of the cam profile, we can just draw it out using a spline which would be going through these points. And this would be the profile of our cam follower. And similarly, if we want the other section, we can do the same thing. So we made a mistake out here. We just did this one and pull it up to this line. Yeah, much better. And we just do this one once again. There's our cam displacement curve. Now we just start drawing, comparing these measurements. So for that, we just start a circle which would be equal to the diameter of the camshaft. That would be 25 millimeters in this case. So this would be 25. Let's just make them coincident. Now we need the prime circle, and this circle is equal to the radius of this base circle plus the radius of the roller circle, and the roller diameter would be 20 millimeter, and so the radius would be 10 millimeters. So the radius of this one is 12.5. So radius of this circle would be 12.5 plus 10, that means 22.5 millimeters, and this is our prime circle. Now we divide this part as similar to the dividations of this region. That means we divide the circle into segments that are equivalent to these dimensions. That means first 120 degrees would be the first segment, then 30 degrees, then 60 degrees. So let's do it. Now we dimension them. And the angular dimension will be 120 degrees. We just make another two lines and dimension them as needed as well. This would be 30 degrees and this would be 60 degrees. They're much better for us. Now we divide this circle as equal amount to the segments as given in this side. So we make the circular pattern. The parameter would be this point and the entity would be this one. The distance would be 120 degrees. We change the direction. The amount would be 6. 1, 2, 3, 4, 5, 6. Yeah, 6 segments as equal to this one. Let's just pull it a little closer. Similar thing for the lowering part, and we just pattern out this one as well. Parameters with this point, entities with this line. This will be 6 degrees. Rotate it. Amount will be 6. 1, 2, 3, 4, 5, 6. 6 segments. That's good enough for us. Now, every single step be equal to the every single step raise of this follower path. So we just measure these points and just make the relationships of them accordingly. So the first point is equivalent to this point, so there would be no direct distance. So we measure these 2 points. Now we measure these distances from this one to this one. It will be 3.35. Keep these relationships as it is, and here we produce a unique type of dimension from this point, and click on this point and press shift and click on this arc. This would be equal to 3.35. This is how things are done. But before that, let's just dimension this one. It was 22.5 into 2. Much better. Similarly, we go for the dimensioning, the other relationships, and do the same thing. And now there is a problem that since these lines were made up of this one, so this dimension is being used for all of these. So I just delete this relationship. Therefore these are free to move, so we make the dimension as these 2 points as 12.5, and similarly the third part, this is 25. We make this one 25 millimeters. Similarly to these two. These two lines give 46.65. Shift this one, 46.65, and the final one B 50. Now another thing, let's just make all these lines as construction lines. Like construction geometry. Our curve would be through these 2 points. So make a spline, connect these points. This is the initial profile. Similarly, since there would be no change in this 30 degrees, so this would be up to this one as well. So we make these 2 points, this one would be 50, and the same thing is happening out here. So I need to delete all the relationships out here as well. So let's just delete all the relationships. Just a second. These triangles will be left except for the patterning ones. So these top points are free to move. Now these descending ones would be equal to these ones. So since this one is equal to this one, so this line should be equal to this line. Similarly, this one equal to this one. And this one would be equal to this line. The final one would be equal to this point. Bring it down here, and the profile would be this one. So I draw another spline. This is our cam profile. Now we hide all the sketch relationships, and let's just set these solid lines, let's turn them into construction lines since we will be extruding them. And we just trim this part out using power trim. There, and our extrusion would be this area. So let's just extrude this. Before that, we just delete this entire sketch because this might cause some kind of problems in extrusion. And just say yes to all, and now extrude the base boss. The contour, just a second, we just forgot to make these construction geometry. Turn them into construction geometry as well, and now go for the extrusion. This is our desired cam. The thickness would be 10 millimeters, good enough for us. And we hide the sketch, and this is the cam that's been described out here. So even though this tutorial is getting a little lengthy, we just followed the standard engineering approach. So this is actually the standard procedure to design a cam. So that would be all for this tutorial. If you enjoyed it, hit the like button below. Please like, share and subscribe. Thanks for watching.